Hey guys, what's up? Welcome back. We are in our triple integrals and we are finishing up triple integrals today with triple integrals in spherical coordinates. Exam coming up on Wednesday. Make sure you're prepared. It's going to be up through applications of double integrals. So it's actually going to be polar coordinates, multivariable functions and their limits, and then double integrals all the way through double integrals or applications of double integrals. So those last few sections are 15.1 through 15.4. And that's everything on the second exam for Wednesday. So just a heads up. Stay in there. We're almost done. Just a few more weeks left of this course. So good job so far. 15.8 today. Triple integrals in spherical coordinates. So triple integrals in spherical coordinates. And before we get to the triple integral part, we want to just talk about spherical coordinates. So first thing to talk about is just spherical coordinates. And last time we went pretty in depth into coordinate systems. We said we have 2D Cartesian, 2D polar, 3D Cartesian, 3D cylindrical. Well, now we have 3D spherical. And that basically says every point in R3 is somewhere on a sphere. So what we're going to do is we're going to say, okay, let's draw the three-dimensional space. You know, normally we have these x, y, and z coordinates like this. So here's x, y, and z. And those are the coordinates we normally use to describe a point. And let's say this is our point. And it would have an x, y, and z coordinate. But now instead what we're going to do is we're going to use some different coordinates. We're going to use this thing called rho, this angle theta, and this angle phi. So now this point is the point we call rho theta phi. So rho is the distance from the origin, theta is the angle off the x-axis, and phi is the angle off of the positive z-axis. So down off the positive z-axis. So rho, the distance from the origin to the point. Theta is the rotation from positive x-axis. And phi is rotation down from positive z-axis. So then we could say, okay, this point is somewhere on a certain sphere of radius rho, centered at the origin. And to get to the point on the sphere, we just rotate theta and phi until we reach the point on the sphere that we want. The rho tells us which sphere, and theta and phi tell us where they are, or where the point is on the sphere. So those are our spherical coordinates. And if you recall that this distance here from cylindrical coordinates we called that R. So that R from cylindrical is actually related to our angles, theta and phi. So that's also the angle phi right there. So what we could say is that sine of phi is equal to opposite R over hypotenuse rho, or we could say R is rho sine phi. So that's one relationship we want to note. And other notes we want to make are that x squared plus y squared plus c squared equals rho squared, since rho is the radius of the sphere. What do we know? We also know that x is equal to r cosine theta, but what is r? R is rho sine phi cosine theta. Y we know is r sine theta, but that's going to be rho sine phi sine theta. And z, well, this is z here. Z is now this side of our triangle. So it's the adjacent to phi. So it's actually that cosine of phi equals z over rho by right triangle trigonometry. Therefore z would be equal to rho cosine of phi. And those are the relationships we want to note. For spherical coordinates. So those are all the transformations we want to make for spherical coordinates. Any questions about the introduction? All right, so let's look at an example. This example says, find the rectangular coordinates of the point rho theta phi, and rho is 8, theta is pi over 3, and phi is pi over 4. Of course, that's always rho theta phi. You'll hear some people say phi for that last letter. That's actually technically more correct Greek, but we don't say p for this letter. We say pi because we already have an English p, so it could get confusing. So although the e sound is correct in Greek, a lot of people just say phi because it kind of blends better with pi. But whatever. I mean, you can say phi if you want. I'm probably going to say phi. So let's look at our relationships here. What do we know? We know x is equal to rho sine phi cosine theta. And so this is going to be 8 sine pi over 4 cosine pi over 3. So that's going to be 8 square root of 2 over 2 times 1/2. which is going to be, let's see, 2 square root of 2. So that's our x-coordinate for this point. Y is going to be 8 sine phi sine theta. Which is equal to 8 sine of pi over 4 sine of pi over 3, which is going to be 8 times square root of 2 over 2 times square root of 3 over 2, which is going to be 2 square roots of 6. And the last one, z, it's going to equal 8 cosine of phi, which is going to be 8 times cosine pi over 4. It's going to be 8 times square root of 2 over 2, which is going to be 4 square roots of 2. So easy enough, I suppose. Hey Ben, welcome, welcome. Glad you made it. A little Calc 3 review for you. All right, another example here. Example, rewrite the equation of the cone z squared equals x squared plus y squared in spherical coordinates. So rewrite the equation of this cone in spherical coordinates. So solution. Probably what we want to do is say that this is going to be z squared equals r squared. And recall that z is rho cosine of phi, and r is rho sine of phi. So that would tell me that rho squared cosine squared phi would be equal to rho squared sine squared phi. And I can cancel the rho squared, which will give me 1 equals sine over cosine is tangent squared, so tangent squared phi. Or sine squared over cosine squared is tangent squared phi. So that means tangent equals tangent phi equals plus or minus 1. Well, if tangent is positive 1, that means phi equals pi over 4. And, or I should say, or phi equals 3 pi over 4. So let's look at that on the graph. So pi over 4 is this angle here, and then regardless of my radius and regardless of the theta value, I get the upper half of the cone. And then the lower half of the cone is 3 pi over 4. So this angle here is pi over 4. And then this angle here is 3 pi over 4. So specifying those two angles then gives us the cone, the complete picture of the cone. This is the cone at 45 degrees, z squared equals x squared plus y squared, or you could just say z equals r, or z squared equals r squared, I should say, to get the top and the bottom half. But that's a nice representation of a cone. In spherical coordinates, for a circular cone, all you have to do is specify an angle phi. Then your theta can rotate all the way around the z-axis, and your rho can go any distance away from the origin, so you get the infinite cone. So phi equals a constant is a cone. So note, whoops. So just a note here. Phi equals a constant is a cone. All right, now let's get into the triple integral part of today. So, triple integrals. And the first thing we want to do is specify the dv element, because we know pretty much everything else that's going to happen, but the triple integral over some solid q f of rho theta phi dv, we want to specify or find the dv element for spherical coordinates. So what we do is we make small cuts in the rho direction, and small cuts in the theta direction, small cuts in a phi direction, and that's going to give us a little differential piece of volume element between two spheres of slightly different radii. So then this length here is delta rho. So that's this length here, delta rho. And we know this length would be rho sine phi. So this arc length here would be rho sine phi delta theta. And then this arc length here would be rho delta phi. So this arc length we already know is the same as this arc length. So then the volume, delta volume, would be length times width times height. And I'll say the length is delta rho, the width is rho sine phi delta theta, and the height I'll say is rho delta phi. So this is going to be rho squared sine phi delta rho delta phi delta theta. So that is our delta volume element, our dv element for spherical coordinates. And that's a geometric derivation. It's really just those arc lengths again. We already know this r right here. This is an arc length at the bottom. And then this is an arc length right here, rho delta phi. And it's approximately a cube. We know, of course, it's not exactly a cube, but if we make those changes small enough, it's approximately a cube. So I could say approximately here. And as those changes go to 0, it does indeed approach a cube. So that's our delta volume, or a dv element. So then all we do is change the integrand, change the bounds, and then put this dv element. So dv is going to be rho squared sine phi d rho d phi d theta for our triple integral. All right, so let's look at an example. Evaluate triple integral over the solid region Q cosine of x squared plus y squared plus z squared to the 3/2 dv, where Q is the unit ball, x squared plus y squared plus z squared less than or equal to 1. So solution. Draw the solid Q, even though here it's pretty easy to visualize. It's just a ball centered at the origin of radius 1. So not too hard to figure out the bounds for rho. Rho goes from 0 to 1. Theta is going all the way around, 0 to 2 pi. Phi goes from 0 to pi. So you can imagine theta goes all the way around the z-axis. And phi goes this way from 0 to pi. If you did phi from 0 to pi over 2 or something like that, that would just give you the top half of the sphere. So to get the bottom half of the sphere, phi needs to go from pi over 2 to pi. And then that will give you the entire sphere. And now we've got integral from 0 to pi. Oh, let's see, 0 to 2 pi. We'll do theta last. Integral 0 to pi. Integral 0 to 1. Cosine of rho squared to the 3/2 rho squared sine phi d rho d phi d theta. So probably want to simplify this a little bit. It's a nice separable integral. So we can first of all say it's integral 0 to 2 pi per theta. So d theta, integral 0 to pi sine phi d phi, integral 0 to 1. And this turns out to be cosine of rho cubed after I simplify that, and then rho squared d rho. And that one's going to do, or it'd be a u sub. So u equals rho cubed, du is 3 rho squared d rho. And if rho equals 0, u equals 0. If rho equals 1, u equals 1. So not much changes as far as the bounds go. But the rest we get 2 pi for theta, negative cosine of phi from 0 to pi, and then times integral 0 to 1 cosine of u du over 3. And this is going to be 2 pi times negative cosine of pi minus negative cosine of 0 times sine of u from 0 to 1 times 1/3. And you'll see that cosine of pi we know is negative 1. So this is negative of negative 1, which is 1 plus 1. So this is going to be 4 pi over 3 times sine of 1 minus sine of 0. But we know sine of 0 is 0. So this is just going to be 4/3 pi times sine of 1. Any questions? All right, look at another example here. Example, it says find the volume of the solid lying inside the sphere x squared plus y squared plus z squared equals 2z, and below, whoops, I should say above or inside the cone z squared equals x squared plus y squared. So again, let's draw this region and then try to figure out the bounds and then do the integral to find the volume. So that's important. We're finding volume, which means we're just going to be doing a triple integral over the solid 1 dv. So it's important to keep that in mind, but let's draw the region. So actually the sphere, we have to complete the square because we have this 2z term. So let's complete the square. X squared plus y squared plus z squared minus 2z. And then we're going to add something to both sides. So plus, what are we going to add? We're going to divide this by 2, get -1, square it, we get +1. So we add 1 to both sides. So this is going to be the sphere, x squared plus y squared plus, and then we have z minus 1 squared equals 1. So it's a sphere of radius 1 shifted up 1. So shifted up 1 unit on the z-axis. So we can graph that. And that would look something like this. So that would be 2, the center point would be 1. So something like that. That would be our sphere right here. And then our cone, we actually just found earlier that the cone, z squared equals r squared, was just the cone phi equals pi over 4, or phi equals 3 pi over 4. Well, 3 pi over 4 is not going to do anything good for us, but pi over 4 is going to be good. So if we stay above or inside that cone, we'll get this nice region for which we can find the volume. So if we just kind of redraw this with only those two regions, we'll get something that looks like an ice cream cone, maybe a little melted, but not too bad. So we'll just try to redraw this ice cream cone. So this is supposed to be a 45, and then this sphere on top. So something like that. So we're trying to find the volume inside this region right here. Okay, well, we've got the region. Now how do we get the bounds? Rho is going to go from the origin out to the sphere, it looks like. So rho is going from 0 to the sphere. Theta is an easy target. It's going from 0 to 2 pi because we're going all the way around the z-axis. And phi is going to go from the z-axis down to the cone, which we already know this cone is the cone pi over 4. So the sphere in spherical coordinates becomes rho squared equals 2 rho cosine of phi. If I rewrite the sphere equation in spherical coordinates, the left side, x squared plus y squared plus z squared, is rho squared. The right side is 2z. Well, that's 2 rho cosine phi. So then I can actually rewrite the sphere equation as rho equals 2 cosine phi. And that's our shifted sphere in spherical coordinates. So that's going to be the upper bound for rho. So 0 less than or equal to rho less than or equal to 2 cosine phi. 0 less than or equal to theta less than or equal to 2 pi. And 0 less than or equal to phi less than or equal to pi over 4. And those are our bounds for our triple integral. All right, so the volume is going to be integral 0 to 2 pi for theta, integral 0 to pi over 4 for phi, integral 0 to 2 cosine phi, and then 1 dv becomes rho squared sine phi d rho d phi d theta. So don't forget, this whole thing is just our dv element. So this is really just us adding up a whole bunch of differential volume elements to get the volume. Again, this is a nice separable integral, so this is going to be integral 0 to 2 pi d theta, integral 0 to pi over 4 sine phi d phi, integral 0 to 2, whoops, not separable, is it? I have to be careful because my bounds for theta, or sorry, my bounds for rho have a phi in them, so that part's not separable. So it's going to be integral 0 to 2 cosine phi, and then rho squared sine phi d rho d phi. So the theta part is separable, but the phi cannot be separated from the rho because of that cosine phi in the bound of rho. So this is going to give us 2 pi times the integral 0 to pi over 4. If I integrate rho, I get rho cubed over 3. So rho cubed over 3 from rho equals 0 to rho equals 2 cosine of phi. And then sine phi d phi. And I can take that 1/3 out. I can say this is 2 pi over 3 integral 0 to pi over 4 8 cosine cubed, if I plug that in for rho. So 8 cosine cubed phi sine phi d phi. And I'll need to do a u sub for this. U equals cosine phi du equals sine negative sine phi d phi. And if phi equals 0, u is cosine of 0, which is 1. And if phi equals pi over 4, u equals square root of 2 over 2. Cosine of pi over 4, which is square root of 2 over 2. So we can simplify the integral after our u sub. I'll pull the 8 out and make it 16 pi over 3. Integral from 1 to square root of 2 over 2. And then u cubed times negative du. So it's going to be 16 pi over 3. I'll use the negative to switch the bounds, and that'll be u to the 4 over 4 from square root of 2 over 2 to 1. And that'll be 16 pi over 3 times 1/4 minus square root of 2 over 2 to the 4th over 4, which will be 16 pi over 3 times 1 over 4 minus, let's see, that'll be square root of 2 to the 4 is 4 over 16 over 4. So it's going to be 16 pi over 3 times 1/4 minus, let's see, that's 1 over 16. So that's actually 16 pi over 3 times 3 over 16, which is pi. So I just found a common denominator here. And that becomes 4 over 16 minus 1 over 16, which is 3 over 16. Any questions? Got one more good example here, and it's going to be that type of example where it's in Cartesian originally, but then it gets pretty nasty if you try to do it in Cartesian. So it'll be one where we take the Cartesian integral and switch it over to spherical. So this last example says evaluate. And we have integral negative 2 to 2, integral 0 to square root 4 minus x squared, integral 0 to square root 4 minus x squared minus y squared. The integrand is x squared plus y squared plus c squared, dz, dy, dx. Now this doesn't mean we can't do it in Cartesian coordinates. It just means to do it in Cartesian coordinates, it's going to be really nasty. You'd have to probably do some trig substitutions. Not going to be fun with multiple variables. So let's try to avoid that as much as possible. So what we're going to do is try to figure out what this region looks like. So from the bounds we're given, we have that z is between 0 and square root of 4 minus x squared minus y squared. And probably at this point you're getting pretty good at identifying what this is already. And if you square both sides, you get z squared is less than or equal to 4 minus x squared minus y squared. Move those x squared, y squared to the left, you get a sphere of radius 2. So it's actually the top half of the sphere of radius 2, centered at the origin. Top half because I take the positive square root right there. So that's why it's the top half. Okay, so that tells us like what the z bounds are. And then the xy bounds, well, y is going from 0 to the square root of 4 minus x squared minus, or 4 is just 4 minus x squared. And x is going from negative 2 to 2. So in the xy direction, it's a semicircle of radius 2. So it's actually this way in the xy direction. And it's kind of set up as like a type 1 xy bounds. So if we graph it in 3 dimensions, this solid is like the top half of a dome, but it's the half that is to the right of the xy plane, or sorry, the xz plane. So let's say negative 2 to 2 in the x direction. And then this way so it's the right half of the dome, right half of the dome. Z less than or equal to square root of 4 minus x squared minus y squared. So the entire hemisphere would have a lower bound for y being negative square root of 4 minus x squared minus, or just 4 minus x squared. But it's the right half of the dome because y is greater than 0. So it's to the right of the xy plane, or sorry, the xz plane. So what are our spherical bounds for this now? Well, rho is not too bad. It goes from 0 to the radius of the sphere because the sphere radius is constant. In this case, it's radius 2. Theta is going from 0 to pi because I'm only going halfway around for theta. And phi is only going from 0 to pi over 2. So don't forget phi comes off the z-axis. So it's from 0 to pi over 2 for phi. So this is actually going to be really easy to translate to spherical coordinates. It's going to be integral 0 to pi for theta, integral 0 to pi over 2 for phi, integral 0 to 2 for rho. And the integrand is rho squared. And the dv is rho squared sine phi d rho d phi d theta. So let's do that integral. This one is indeed a nice separable integral because all the bounds are constant. So integral 0 to pi d theta, integral 0 to pi over 2 sine phi d phi, integral 0 to 2 rho to the 4 d rho. And this is going to be pi times negative cosine of phi from 0 to pi over 2 times rho to the 5th over 5 from 0 to 2. And that's going to be pi times negative cosine of pi over 2 is 0, so 0 minus negative 1 times 32 over 5. And this is just going to be 32 pi over 5 after we reduce everything. Or I should just say multiply everything. Is there any questions about that one? All right, so it's going to take a lot of practice to get used to trying to figure out how to find the bounds for these spherical coordinate integrals. But usually what happens is once you change it to spherical coordinates, it becomes a lot easier. The integrand becomes easier if there is one, or if you're trying to find volume, it's a lot more doable. It just, things typically get nicer when you switch to spherical coordinates, but only if your region of integration has some kind of spherical property or something that's really nice for spherical coordinates, like a cone or a sphere. You don't probably want to use spherical coordinates for like boxes and paraboloids and cylinders and hyperbolic stuff. Like, it's more for spherical stuff and cones and stuff like that. So that's kind of the idea, is the name of the coordinate system kind of tells you the regions of integration you kind of want to focus on. So cylindrical coordinates is for stuff that has like nice cylindrical symmetries, like hyperboloids and cylinders, possibly cones and spheres, but spherical coordinates are probably best for spheres and cones and things like that. So there are some problems in web work where you could use either coordinate system, and you'll find out that one is a lot more work than the other. So I'll let you go through that and try to get a handle on, when is it better to use one coordinate system than the other. But yeah. Any questions before we call it a day? All right, I guess we'll just call it a day, and you guys get studying for the exam. I'll see you next time. Have a good afternoon.